Welcome back. Let us start with the next module in this microprocessors and microcontrollers. Today I will be dealing with memory interfacing to 8086. So a few basics. The first thing that we are talking about is the semiconductor memories. And as we know, there are different types of memories. We can say that the generic ones are RAM and ROM. And basically RAM is used to store the data, whereas the ROM to store program. If you use ROM, it's an OTP. OTP is one-time programmable device. Basically, I would like to write the program again and again. In that case, the RAM is replaced by an EEPROM or a flash. Coming to the signals that are associated with the memory device, we have the address lines A0 to AX, the data lines D0 to D7 or D15 or D31 depending on the length. Then the control signals CS, read and write. In this session, basically the learning objectives I have divided into three parts. The first is the memory organization and the characteristics of a memory device. Then later I will be talking about the assignment of memory address to a memory chip. Then the different address decoding techniques. So three things, that is the characteristics, then assignment of memory address and decoding of memory address. In any computer or a processor, the CPU has to interface with a device, a memory device, basically a RAM, and this interfacing we are targeting. The second part we will be targeting the IO processor after 2 hours. Then coming to the memory is the storage element in the computing system. It stores the codes for the sequence of instructions, and hence you can say it's a primary storage for code. Along with the sequence of the codes, it also has to store the data on which it has to execute. So the memory consists of the storage for code as well as data. Coming to the construction of a memory device, it's a device as we seen, it can store either a digit 0 or 1. And the basic unit is a flip-flop. It can be a charge in a capacitor also. And if it's a flip-flop, it can store a 0 or 1. This is your typical flip-flop here, a JK flip-flop. And this is later replaced by a data flip-flop, D flip-flop, which can store a 0 or 1. And this unit, let me say call this as a memory cell. An array of these memory cells arranged in the form of a shift register is, let me say, the word. So basically a word consists of an array of this memory cells. In this example that we have given here, let us see cell 1, cell 2, cell 3, 5 cells are there. These are arranged as a parallel in, parallel out. That is, I can write in the data at JK and read the data at Q. And this group of flip-flops is known as a word. And the number of cells in this group of flip-flops defines the word length of the memory chip. In this example, I have C1 to C5, so the word length is 5. In any computer, the word length is generally arranged as 1 for DRAMs or 4, 8, 16 or 32 in that order. And every array of flip-flops here, this I can call it as a word, a single memory word. You can see that there are input lines I1 to I5 at which they are equivalent to this J part here or D part here for a D flip-flop. wherein you write the data, and to read the data you read it at O0 to O5. So you get a data in and a data out, and these enabling this group of flip-flops together, or enabling this particular word, is through a memory address. So what do you mean by this memory address? As I said, a memory will have many words. Each word is, let me call it as a location. In this example here we have shown there are 3 locations. This is location 0, location 1, location 2. 3 locations. Each location is consisting of 5 flip-flops, or I can say 5 memory cells. And what is the capacity of this? There are 3 words. So there are 3 words, and each word is having 5. Each word can store 5 bits. So total capacity in bits is 15 bits. And the number of bits that a semiconductor memory can store is called as chip capacity. The chip capacity is defined in kilobits or megabits. Kilobits is basically 2 to the power 10 or 1024, whereas megabits is 2 to the power 20. So this is different from your basic K. K represents 1000, that is 10 to the power 3, but here the kilobits is in terms of 2 to the power 10, which is 1024. And also the storage capacity of a memory chip is given in bits, whereas that of a computing system is given in byte. As we know, 1 byte is equal to 8 bits. So we can define the memory capacity or the chip capacity in terms of bits or bytes, and if it's in terms of bits, it will be like 2 to the power of 10, that is kilobits or megabits. And if it's in the in terms of bytes, the whole thing, whatever you have, the chip capacity in bits has to be divided by 8. Apart from the memory capacity, you also need 2 more operations, that is a read or a write operation. When I'm talking about a RAM can read and write. So I have a read signal to enable reading. When you say a read signal, whatever data is stored in the memory cells are put on the data lines. Here the data lines are O1 to O5. Whatever is stored in C1 to C5 will be put on O1 to O5. That is read operation. When you say write operation, whatever data is there on the input lines I1 to I5 are taken inside the memory. They will be stored in the memory. Basically, this I1 to I5 or O1 to O5, they are connected to a bidirectional data bus D0 to D5, and here there are 5, so the data lines are 5. As such, the data lines are arranged in multiples of 8. When you talk about ROM has only one operation, that is read operation, and the read operation is also known as output enable. For a RAM, we have 2 operations, where they are read and write. For a ROM, only one operation, that is read. Whatever data is already stored, generally the code will be read. And next comes the addressing. We need address lines. And why do we need this address line? As I said, the memory is arranged in the form of words, and each word is having an array of memory cells. And let me take this example once again. Here there are 3 locations. To address these locations, we need address lines. Say I have only one address line A0. This address line A0 can take values of either 0 or 1. So if it is 0, it will address one location, and if A0 is 1, it will enable the second memory location. So 2 address lines are not sufficient. So I have to take one address line is not sufficient, as one address line has only 2 values. Whereas if I take 2 address lines, let us say A0, A1, these 2 address lines together can have 4 combinations. What are the 4 combinations? 00, 01, 10 and 11. So each can be one particular location. The combination 00 is known as a start address. So in the memory chip, the first location is having an address 00, and that will be known as a start address. And the last location will have an address 11, that is known as a end address. So in any memory, in any memory, we will be having k address lines. So in the previous example here we have 2 address lines. So extending further, a memory will have k address lines. If it has k address lines, how many locations it can access? It can address 2 to the power k memory locations. As we have seen here, we have 2 address lines, so 2 to the power 2 is 4 locations. Similarly, for k address lines, we can have 2 to the power k memory locations. And so if I have a RAM with k address lines and n data lines, these data lines are used to read in and out the data. For example, here how many data lines are there? 5 data lines are there, O1 to O5. Each one, remember, is one cell. Each one can store a 0 or 1. Suppose there are n address line, n data lines here, and k address lines. Totally, what will be the capacity? So how many locations we can have because of k address lines? 2 to the power k, and each location will have 8 cells, or it can store let me say n data bits. So total size will be 2 to the power k into n. And what is this 2 to the power k into n? This is known as a capacity of the ROM. And this organization, the other word is organization, wherein it is organized as n data lines, and each location will be having n data. And how many such locations you can have? 2 to the power k. So the second important characteristics is the organization. The first important characteristics is your capacity, and the capacity we have seen. What's the capacity? Chip capacity is the total number of bits or bytes it can store. And the second characteristics that we have studied is the organization. And how is the memory organized? It's organized with n data lines and k address lines. Apart from this, we also have the control lines, read and write, we have seen. And now how does this read and write define? They define the third characteristics, that is known as the access. Okay, that's the speed of access. Let me look at the operation to access the data. To read the data that is stored in a particular location, what do? We first place the address on the address pins. So we have the address pins. So place the address on the address pins. Then activate the read pin. As soon as we activate the read pin, whatever is stored in the memory will be put on the output lines. But this is not immediate. A certain amount of time is required, and this amount of time defines what is known as the access time. And the access time can be as small as a few nanoseconds and to as high as hundreds of nanoseconds. And if it's a fast memory, the access time is very less. As soon as you place the address on the address lines, I get the data on the data lines. So the third characteristic that we are talking about is the speed. So the three important characteristics: capacity, organization, and speed. And this is a small example which tells you the difference between organization and capacity. Let us consider a memory chip which has 12 address lines and 8 data pins. So the organization is 2 to the power 12, that is 2 to the power of number of address lines into 8. What is 8 here? 8 is the number of data line or data pins that are available. So total capacity is 2 to the power 12 into 8, and you can write it as 2 to the power 12 into bytes. As I said, the capacity can be in terms of bits and bytes. So in terms of bytes, if you define, it is 2 to the power 12 bytes. And if I had to express it in another way, I can just say this 2 to the power 12 bytes, I have to express it in kilobits or kilobytes. 2 to the power 12, you split up into two parts, 2 to the power 2 into 2 to the power 10. Total 2 plus 10, 12 bytes, and this 2 power 2 is 4 and 2 power 10 is k. So remember, 2 power 10 is kilo, that is 1024. So the total capacity will be 4k bytes. So recapping, what is 4k bytes? 4 is 2 power 2 and k is 2 power 10. And what about 8 here? 8 is each location will have 8 data, and that is given as 4k bytes. Same capacity, instead of saying in terms of bytes, we can express it in terms of bits. To express it in terms of bits, whatever we have, 2 power 12 into 8, express it as 8 is 2 power 3. So 2 power 12 into 2 power 3 is 2 power 15 bits. Now split up 2 power 5 into 2 power 10. So this 2 power 5 is 32 and 2 power 10 is k. So the total capacity is 32k bits. Or capacity in bytes, as we know, is how much? 2 power 12 or 32 kilobits. We have the capacity in bytes already. That you multiply by 8, I get the capacity in bits. So the various ways of calculating the capacity. So this is an example where we have calculated in terms of bytes directly first, then converted it into capacity in bits, and the same whatever we have in capacity in bits, if we have to go back to capacity in bytes, 32k divided by 8, I get 4k, or 4k I have capacity in bytes. To get it in terms of bits, this 4k multiplied by 8, I get 32k bits. So a same example wherein have 12 address lines and 8 data pins, we have shown the organization and the capacity. And these are some basically commonly available RAM chips and ROM chips. The chip name will define the type, whether it is static RAM or dynamic RAM, and the capacity and the organization and the speed. So any data sheet gives you these three important things: the type, whether it is SRAM or DRAM, and the capacity, organization and speed for RAM. Similarly for ROM, the type, whether it's an EEPROM device or EEPROM or a flash device, and the capacity and the organization and speed. So let us take small examples here. 2k, what is 16k? 16k is the capacity of this 2716 chip. And how is it organized? It is organized as 2k into 8 with a speed of 450 nanoseconds. The same UV EEPROM, another chip, will have 32k, and what is the organization? 4k into 8. So 4k into 8 is the organization, and this capacity is in terms of bits. And these are the various examples. It's an increasing order from kilo to megabits. So the three important characteristics of memory are capacity, organization and speed. And this memory, whatever you have, has k address lines and n data lines. And what will be the organization? 2 to the power k, there's an address line, into n. Few more examples. Let us say I have a 4k ROM and find the address range for this 4k. 4k expand, it is 2 to the power 12, 4 is 2 power 2, k is 2 power 10, so it's 2 to the power 12. It requires 12 address lines. And for the 12 address lines, if the address line starts from A0, it will be A0 to A11. A0 to A11 are 12 address lines, and if these 12 address lines take the values from 000 to 111 and I group 4 together, the total range will be 00 to 0FF. We will see this better when we do a little further memory map. So basically 16k, another example, 16k you define it as 2 to the power 4k. So I need 14 address lines, and what are the 14 address lines? A0 to A13. Including A0 to A13, total how many address lines we have? 14 address lines. And total address range will be this, that is the start address to end address. And similarly you can see 32k. And until now we are talking about the basic memory organization, a device, and in the device how many address lines we have, how many data lines we have, and what are the control signals. If this memory device, let us say a RAM or ROM, has to be interfaced to a processor, and the processor that we are studying here is 8086 processor, how do we interface? Let us look at the 8086 address range. The 8086 has 20 address lines or 20 address pins. The address pins are A0 to A19. With this 20 address lines, how many locations it can access? It can access 2 power 20 locations, or 1 mega addresses it can access. So the address range for 8086 is 1 mega. And how did we get 1 mega? Because it has 20 address pins, and these 20 address pins are A0 to A19. And when I look at this RAM or ROM, let us take an example of this ROM with 7 address lines, A0 to A6. With this 7 address lines, this RAM or ROM has how many locations? 127 or 128 locations it will have. This 8086 can access 1 mega addresses, whereas this RAM or ROM needs only 128 locations or 127 locations. So this entire thing is not needed. Only a small part of this address is sufficient. Out of 1 mega addresses, only 128 locations are sufficient for this RAM and ROM. So how do you splice this? How do you cut it into pieces? And this piece of address you assign it to this RAM or ROM. For that we need memory address decoding. So what do you mean by memory address decoding? The processor usually addresses a memory space that is much larger than the memory space covered by an individual memory chip. So here the processor that we are talking about is 8086. It will address a memory space. How much memory space it is addressing? 1 mega address. But the memory space covered by this individual memory chip here is only 128 locations. And since this is so, we have to splice the memory device into the address space of the processor. And to splice this, we need this memory address decoding. And how do we go about this memory address decoding? We generally use a decoding circuit, and required address lines A0 to A6 are directly connected to the RAM or ROM. And we have the control signals. The two control signals are OE and WR. That is OE because OE is output enable or read. So we connect the memory read signal from 8086 to the OE, then the memory write signal to WR. What about the data lines? The data lines are directly connected to the RAM or ROM. That again we'll see in the second part. At present we are just looking at the address and the control lines. So two control lines are required. The two controls are memory read and memory write. Then coming to the address, so A0 to A6 are required for the RAM or ROM for this specific example. The remaining address lines A7 to A19 are decoded using a decoding circuit, and that is given to the chip enable or chip select. So only when the chip select or chip enable is activated, these address lines A0 to A6, the address on this will locate a location in this RAM or ROM. So if this is not activated, even if there is data on A0 to A6, this memory is not enabled. So the basic connection is the data bus is connected directly to the data pins of the chip. Then the control signals read and write are connected to the output enable and write enable we have seen, and the lower bits of 8086 address lines are connected directly to the memory chip address pins. So which are the lower bits? We have just seen A0 to A6. Then what about the higher bits? The higher bits are used with a logic circuit to activate the chip select of the memory chip. So now to do the decoding circuitry, first let us look at finding out how many address lines are required for accessing the data. This, as I said, it depends on the memory capacity. Now if the memory capacity is 512 bytes of RAM, how many address lines are required? 512, express it as powers of 2, it is 2 to the power 9, and so we need 9 address lines. And what are the 9 address lines? A0 to A8. And if I increase it to 8K, the 8K is 2 to the power 13, so 13 address lines. So which are the 13 address lines? A0 to A12. So the decoding, as I said, there are many types. The first simple decoding is with logic gates. The simplest logic gate is a NAND gate. The chip select is generally active low, and the NAND gate output is also low. So this can be used directly, the NAND gate output can be used directly to the chip select, or in some cases you can also activate this if it's a RAM with a read or a memory read from this. So the address line, as I said, is connected directly to the RAM. We'll take a specific example once again. How do we decode with a NAND gate? This example interfaces a 4K memory chip to the 8086. So since it is 4K, if I consider it is 2 to the power 12, so we need 12 address lines. And what are the 12 address lines? A0 to A11, the lower bits, and the remaining lines A12 to A19. So these are my A12 to A19. They are given to a NAND gate, and the output of the NAND gate is given to the chip select. So this is your EEPROM. So we have the memory read given to OE bar, output enable, then the data lines that are directly connected to the processor, and the address lines are split into two parts. The address lines required for EEPROM depending on its capacity. So for this capacity of 4K, the address lines are A0 to A11, that is given directly, and the remaining ones, what are the remaining ones? A12 to A19. A12 to A19 through a NAND gate are given to chip select. Since we are using all the remaining address lines, address pins, it is known as full decoding. So this is an example of full decoding, and here in this example already the interfacing circuitry is given. We are supposed to find the range of the addresses. So what is given? It's a 32K RAM, so it's 32K into 8 RAM. And as we know, 32K, what is 32K? 32K is 32 is 2 to the power 5, 2 to the power 5 into 2 to the power 10, so totally 2 power 15 or 15 address lines are required. So the 15 address lines are A0 to A14. So as I said, this A0 to A14 depends on the capacity of the RAM. The remaining lines, what are the remaining lines? A15 to A19. A15 to A19 are given through a NAND gate to the chip select, And how are they given? A19 is connected directly, even A18 is connected directly, whereas A17 and A15 are given through an inverter to the NAND gate. So for this combination of inverters and NAND gate, how do we determine the address range? So for this we have to write the memory map. So how do we construct the memory map? The memory map will be from A0 to A19. Remember, your 8086 processor has 20 address lines, and what are the 20 address lines? A0 to A19. In this A0 to A19, only A0 to A14 are required for this RAM. 32K. 32K means A0 to A14. So these black ones, that is the A0 to A14, can take all the values. What are all the values it can take? From all zeros to all ones. So each combination on A0 to A14 will access one location in the memory. The remaining address lines, what are the remaining address lines? A15 to A19. So this A15 to A19, they do not change. A19 is 1 and A18 is 1 and 17 is 0 because it is given by through an inverter. 16 is 1 and 15 is through an inverter. So to access this RAM, access any location in this RAM, we have to change this A0 to A14. Apart from this, the chip select also has to be enabled. This chip select is enabled only if the NAND gate is low. This NAND gate, output of the NAND gate is low only for this combination of A15 to A19. The combination of A15 to A19 is 11010. So what's the combination? 11010 from A19 to A15. So if this combination is kept constant and if this A0 to A14 is varied, what will happen? Different locations in the RAM are enabled. And what are the range for which this RAM is enabled? So now take the same memory map wherein I have shown the start address and end address. Now you split it into 4 bits together, merge 4 bits. So A0 to A3 is one hexadecimal digit, that value is 0. A4 to A7 is another hexadecimal digit, 0, and this is 0, this is 0. Then remaining A16 to A19 is 1101. So what is 1101? 8, 4 and 1. 8 plus 4, 12 plus 1, 13, and 13 is D, hexadecimal D. So the start address is D followed with 4 zeros. D followed with 4 zeros gives the start address of this 32K RAM. Similarly, the end address. So what is the last location in the RAM? The last location in this RAM happens when all these address lines are 111. When all these address lines are 111, again group it 4 together. These 4 bits is F, and these 4 bits is F, and here only A12, A13, A14 can become 111. Whereas A15 is given to the chip select, A15 is given to the chip select, and that remains as 0. And this A19 also will remain as it is, and when I club all this together, this will become 7 and this will become D. So the end address of this RAM is D7FFF. D7FFF. So the range of this is from D4 zeros to D7FFF. And how did we get this? First, separate out the address lines required by the RAM. It is from A0 to A14, and remember, this depends on the capacity of the RAM, and this A0 to A14 can change from all zeros to all ones. And the remaining address lines A15 to A19, this combination depends on how you give to the input of the NAND gate. And all of them should be high, all the inputs should be high, only then the active or low output we get. So how do we get this? We get this as 1, 1, and if this is 0, it will be 1, this is 1, A15 if it is 0, this will be 1. So these combination of 1, 1, 0, 1, 0 will activate the NAND gate. So this is an example of full decoding. Now let us take the next example of partial decoding. So what do you mean by partial decoding? Partial decoding happens when I don't use a complete 1 mega. Only 1 or 2 small memory devices, I interface it to the processor, and I try to reduce my decoding complexity. So the same example, let us say here, this is an example. A11 to A15 are used to select the CS bar, and A11 to A15, what combination should it be? A11 is 0, then A11 is 1, A12 is 1, A13 is 0, this is 1, and this is 0. Wherever you have an inverter, this should be 0, so that this becomes 1. So when all are 1s at the input of the NAND gate, the output of the NAND gate will be 0 or active 0, and that will enable the chip select CS bar. So once again, when I write the memory map for this, this is from A11 to A15. 1, A11 is 1, A12 is 1, A13 0. 2 inverters, one is A13 and the other is A15, so both of them should be 0, 0. The rest are 1s. So this is the chip select portion, and this is kept constant. And the lower address lines, after A11, what is the lower address lines? A10 to A0. Now these lower address lines can take all the values from all zeros to all ones. And once again here, when I split it into 4, so the start address, these 4 zeros 0, this 4 zeros 0, and here this A8, A7, A10, A11, these 4 together if I group, I get 8, and remaining 0, 1, 0, 1, this is 5. Then the end address, the lower address lines A0 to A11, A10 are made all ones, and when you group them together, you get 5 triple F. So this is a range for the basic RAM. But in 8086, I have address lines, it doesn't stop at A15. It goes to A16, 17 till 19. So the remaining address lines, which are the remaining address lines A16 to A19, they are not used in the NAND gate. And though they are not used in the NAND gate, this will work but this will work even for different combinations of A16 to A19. So if suppose if this A16 to A19 are 00, all fours are 0, the basic address range will be 05800 to 0805 or triple F. So these four, A19 to A16, instead of being all zeros, they can be any other. Let us say they can be 3. If this is the 30011, then the address range is 35800. This 3 is not connected anywhere, but this 5 will activate this, and a 5800 will activate a location. So whether it is 05800, 35800, 25, E5, anything, any combination, they will all select the 5800 location. So multiple addresses will select the same location, which is the location 5800. So this aliasing effect comes into picture when we are doing partial decoding. Only advantage of partial decoding is the number of input lines of your NAND gate reduces. The number of input lines to a NAND gate reduces, but it will lead to multiple addresses. Multiple addresses will also locate the same location. Then we have the next example is using this logic gate as a decoder interfacing a RAM and ROM. Specific examples from your textbook. So this is my 32K into 8, and these are the lines A0 to A14 required to access this 32K. And since it's a RAM, it will have two control signals. The two control signals are output enable and write bar. Both of them should be given to memory read and memory write respectively. And this is your logic gate. Basic logic gates of NAND and inverters. Both of them are activating CS bar. This gets activated for this combination. Can you see only A15 is high, the rest are all low, A16 to 17. So when I write once again the memory map for this, so A0 to A14, they will vary from all zeros to all ones. They are the different locations in this RAM. The remaining portion, which is used for chip select, they should be kept constant. So A15 will be 1 and A19 to A16 are all zeros, and this when I repeat for the end address, I get the range. So this is 0, this is 8, and this is my starting address, and once again this is 0, these are all ones, these 0F, 4Fs are the ending address. So there is a range of this particular example. One more example wherein you have the same NAND gate, it's interfacing a ROM. The only difference is in the previous example you have two control signals, output enable and write bar. Here since it is a ROM, the read bar signal is known as output enable, so only one signal that we have. And once again you have a NAND gate here activating the CS bar. The capacity of this is 64K. So 64K is 2 power 6 into 2 power 10. So it requires 16 address lines, and the 16 address lines are A0 to A15. In the previous example I had A0 to A14 for 32K, and this example 64K, so the address lines are A0 to A15. They are all black. The rest A16 to A19 are in red, showing that they are the control line inputs. And here A16 is 1, then A19 is 1, the rest through inverters A17 and A18s are 0 0. And when we split this once again as a start and end, I get the range. This is 9 and all zeros, and for the end address where all of them are ones, this is 9 with followed by 4 Fs. We can simplify. Remember, if I have to interface one more memory device, I require one more NAND gate with the necessary inverters, etc. I can reduce the number of NAND gates and the complexity of this decoding circuitry if I use a decoder. The basic decoder we consider is 74LS138. This, as you know, it's a 3x8 decoder. In this 3x8 decoder, we have 3 decoding inputs, 3 inputs, select lines, you call it as A, B, C. These are the 3 inputs. It's a 3 input, and that will be decoded into 8 outputs, Y0 to Y7. If this combination on A, B, C is all 0, 0, 0, Y0 is activated. Y0 becomes low. These are active low outputs. Since they are active low outputs, they can be connected directly to the CS bar pins. And if the combination of ABC changes, the one more output will get activated. So one among these 8 output lines will get activated depending on the ABC. Apart from this ABC, here we also have some more enable lines, G1 and G2. G1 is active high and G2 is active low. Even they should be enabled, only then the data on, the chip select on ABC will be generated. The advantage of this address decoding using decoders is it will avoid uses of multiple NAND and inverter gates. So as I said, we'll look at the function table of this decoder IC. It has Y0 to Y7 and only one will be activated. Can you see that ABC is all lows? So only Y0 is low, the rest are all high. And similarly, when this is 001, ABC are 001, the Y1 is activated. For Y2, this is 010 and so on. So this table from here 00 to 11 on the combinations of ABC will be reflected on the output lines. So Y0, Y1, Y2, Y3 till Y7. They are active low, the rest are all high. And for this to get activated, what about the enable signals G1 and G2? As I said, G1 is straight, so it should be high. G2A and G2B are through inverters, so they should be low. So G1 should be high and G2 will be low. And this combination along with this ABC, will select Y0 to Y7. By chance G1 is low or G2 is high, then this chip is not activated. None of the output lines are activated. So to get an output on Y0, apart from ABC being 000, G1 should be high and G2 should be low. So let us look at an example wherein I have a decoder IC and Y4, the decoder IC is connected to a memory chip. The memory chip that you consider is 64K into 8 ROM. As you said, 64K will have address lines from A0 to A15. And to enable this chip, Y4 is connected to this. And Y4, as you know, is enabled when ABC are 0100. So 4 is 100. So Y4 is enabled when C is 1, B and A are 00. And what about A19? A19 is connected to G1 and we are seeing G1 is active high whereas G2 are active low, but here G2 effect is not there because G2 is permanently grounded. So this G1 is A19 and that should be high to activate this. So A19 is 1 and this ABC, these ABC are 16, 17, 18, the ABC should be 100. Or you can say that CBA. So the CBA is 100. So the start address of this, is C. A19 1, then C is 1 because CBA is A18, A17, A16. So this is 100. And then what about A19? A19 is connected to G1 and that should be 1. G1 is active high and that should be 1. So total address is C and remaining A15 to A0. The remaining A15 to A0 can be all zeros or they can be all ones. So if they're all zeros, this is 4 zeros, and if they're all ones, these are 4 Fs. So the total address range for this start address and end address is C followed with 4 zeros and C followed with 4 Fs. So we can also do another way around. Suppose the start address and end address is given. So how do we compute the capacity? So to compute the capacity, subtract end address minus start address. So if you add 1, end address minus start address gives me 4f's, and to this 4f's, if you put plus 1, it will become 1 followed by 4 zeros, and 1 is at a 2 to the power 16 place. And what is 2 to the power 16? 2 to the power of 16, you split it into 2 parts, 2 power 6 into 2 power 10. So 2 power 6 is 64, 2 power 10 is k. So to compute the capacity of the memory, if start address and end address are given, the procedure is take the end address, from the end address subtract the start address. So here C 4f's minus C with 4 zeros gives me 4f's, and to this you add 1. So 4f's plus 1 becomes 1 followed by 4 zeros hexadecimal, and that 1 is in the place of a to the power 16, and that is 2 to the power 16. So this is one more example, last example. Here basically you have a change, A16, A17, A18. Similarly here instead of A16, A17, A18, you can see it is A14, A15, A16, because the 64K ROM is replaced by a 16K ROM. Once you replace with a lower capacity, for 64K we needed A0 to A15, whereas for this 16K I need only from A0 to A13, and A0 to A13 is from the remaining address lines. The remaining address lines are A14 to A19. And how do we arrange these remaining address lines? So I connect A14 here, A15, A16 straight, then A17. Previous example we had to take care of only 4 address lines, which are the A16 to A19 remaining. But here I have more number of remaining address lines, so we can arrange them. How do we arrange them? Either we can connect them straight or we can connect them through an inverter. So with all this, so totally how many upper address lines I can activate? 6 upper address lines, that is A14 to A19. So let us look, when is this Y4 activated? When is this Y4 activated? This is activated for A14 0, A15 0, A16 1. So 1 0 0 activates Y4. Along with this 1 0 0, what about A17? This is active low. A17 should be 0. A18 also should be 0. What about A19? A19 is active high, it should be 1. So the chip select lines, what are the chip select lines? 1 0 0, and this is for Y4. For Y4, ABC should be 1 0 0. 1 0 0. So the chip select lines, based on this, now construct the memory map and find the start address and the end address. So in the memory map, as we see, this A15 to A13 it will take care, A19 to A14 it will take care, A13 to A0 will change. Now it's a homework. Instead of Y4, suppose I give it to Y7. If you give it to Y7, which are the address lines it will get activated? For which address lines it will activated? These remain same. A19 should be 1, A18 should be 0, A17 should be 0. But what about ABC? For 7, ABC should be 1 1 1. So if all three are ones, and this is 0 0 and this is 1, then Y7 gets activated. So then you can compute the address ranges. Okay, now thank you. So in this session we had done the basic memory organization, the parameters of a memory chip, and the 3 types of memory address decoding, that is full decoding, partial decoding, and decoding with a decoder. And in the next class we will be looking at interfacing to the 16-bit microprocessor, that is 8086. How do we have here, till now we are talking about only one memory chip. Tomorrow we will be talking about many memory chips, like 5 or 6 memory chips with the different address range and the complete decoding circuitry. Thank you.